Good morning. Today we are going to study about hydrogen spectrum. We already studied the Bohr atom model. From that we got an expression for energy also. Energy, the frequency of the emitted radiation, isn't it? So here we are going to study the hydrogen spectrum in detail. See what happens when white light is passed through a prism. You know that process is known as dispersion. That means splitting up of component colors. So here you can see that when white light is passed through prism, the white light consists of 7 colors and that 7 components are seen here. So when white light, which is made up of all the colors of the visible spectrum, passed through a prism, all the colors gets separated. What happens if the light is not white? How can we obtain the spectrum? So coming back to the previous slide, what do you mean by spectrum? Here you can see this visible spectrum contains 7 colors. So here you can see the distribution of continuum of all the radiant energies. See, the white light which contains all the 7 colors is get distributed continuously. And this distribution can be plotted either as a function of wavelength or frequency. In a chart is known as spectrum. I repeat, when white light is passed through a prism, we get the spectrum of a white light. So what does it mean? We got the distribution of continuum of radiant energy, which is plotted either as a function of frequency or wavelength in a chart is known as spectrum. So if the light is not white, how can we get the spectrum of that light? We can heat that gas. So by heating a gas or with electricity, it will emit its colors. And what happens if we pass this light through a prism? Let's see. See, here we have a white light and we passed it through a prism. So we got a continuous spectrum. We are photographing the individual colors which is coming out of the prism, and in that photograph we will get like this. So it is a continuous spectrum, isn't it? Now what happens if we are taking hydrogen gas? Why we are taking hydrogen gas? We are studying about hydrogen spectrum, isn't it? So we are taking hydrogen gas inside a discharge tube and we are heating it. So what happens when it gets heated? It will emit radiations or light, and if we are passing that light through a prism, we will get something like this, which is known as emission spectrum, or we will get like this, a dark lines in bright background, which is known as absorption spectrum, and white lines in black background, that is emission spectrum. So, in order to study hydrogen spectrum, which can be either emission spectrum or absorption spectrum, we are taking hydrogen gas inside a discharge tube. And the light emitted by this hydrogen gas when electricity is passed through it is studied with the help of a prism by passing that light through the prism, so that we are getting either emission spectrum or absorption spectrum. Why we are studying atomic spectrum? Atomic spectrum is the fingerprints of an atom. What does it mean? So by getting the spectrum of an element, we can identify the atom and we can get the very basic informations about the atom. So we are studying atomic spectrum in order to identify the atom and also get information about the atom. See, here you can see several spectrum of hydrogen, neon and iron. How can an iron emit light? See, you can take a piece of iron, a long piece of an iron, and you can put it into on a fire. What happens to the end of the iron that is in the fire? It starts glowing, isn't it? Glowing means glowing in different colors. Sometimes it becomes yellow, sometimes it becomes red hot, isn't it? That means it is emitting its energy or emitting radiations. So the light is emitted. So such a spectrum are known as line emission spectrum. So the light is emitted from the iron and this light is studied or this light is photographed, and such spectrum are known as line emission spectrum. Now, with the help of Bohr, we had calculated the expression for the wave number as well as frequency of the emitted lines. See, whenever an electron jumps from one state to another state, what happens? It will either emit or absorb energy, and it will emit a radiation. And we have calculated the formula for the frequency of the emitted radiation. So here we have got the expression for nu bar, that is wave number, which is r into 1 by n1 square minus 1 by n2 square, where r is the Rydberg constant. Now, how Bohr explained the hydrogen spectrum? So we started to study the hydrogen spectrum. So in order to study hydrogen spectrum, we took hydrogen gas in a discharge tube and we allow the current to pass through it at a low pressure. So what happens to the hydrogen gas? The hydrogen molecules will split into hydrogen atoms. So here you can see that a H2 gas on undergoing low pressure and electrical discharge, it splits into hydrogen atoms, 2 H atoms. These atoms will absorb energy from the electric spark. So the atoms are absorbing energy. What happens to the electrons of the atom? The electrons on getting energy will excite to the higher energy states. See here, the ground state electron is excited to the first excited state, or the electron can jump into the second excited state if it's getting more energy. See, when one photon gets emitted on electron, it gets jump into the first excited state. If the electron is getting 2 photons, what happens? The electrons are jumping into higher energy level, higher excited state. So electron of the hydrogen atoms are excited to higher energy levels, and the higher energy level orbits to which electron migrate will depend upon the amount of energy absorbed by the electron. So I repeat, in order to get a hydrogen spectrum, we took a hydrogen gas, and under low pressure the hydrogen gas split into hydrogen atoms, and these atoms absorbs energy from the electric spark. On getting energy, the electrons jump into the higher energy states depending upon the amount of energy they got. Now these excited electrons will not be stable there. Why? These electrons are having high energy and they have a natural tendency to have low energy. So what will they do with this more energy, excess energy? They will dissipate the excess energy and will try to come back to it the lower energy levels. See, here in the previous slide we had seen that this electron on attaining one photon gets jump into the high first excited state. Now here what happens to that electron? That electron emits that photon and will come back to the lower energy state. And what about the second electron? Second electron on attaining more energy is jumped to the second excited state. From there, that electron first emit the first photon and come back to the first excited state, then against the next photon, again emits the next photon also, and again come back to the ground state. So what happens? The electron emits energy here. Here the electrons absorbs energy. So whenever the electron absorbs energy, we can take the photo of the hydrogen gas which is coming out of that discharge tube, isn't it? So we get an absorption spectrum. Now when the atom emits energy, what happens? The radiation is given out. So we can photograph that. So that will be the emission spectrum of the hydrogen. Clear? So this is the picture showing the hydrogen spectrum. So here the hydrogen gas is taken in a tube and a high voltage is applied. So what happens? Hydrogen gas split into atoms. These atoms either will absorb the energy and will go to the higher excited state, and from there they will come back to the lower energy state by emitting energy. So these, whenever they emit radiation or that radiation is passed through a slit and it gets passed through prism, so its component colors are photographed in a photographic plate. That photograph is what we now call it as line spectrum of hydrogen. See, the line spectrum of hydrogen that contains several spectral lines having particular wavelength. See, here the distribution is shown in terms of wavelength, isn't it? 410 nanometer, 434 nanometer, 486 nanometer. So this is the wavelength of the light given by the hydrogen. So this is the line spectrum for hydrogen in terms of wavelength. Clear? Now we can also calculate the wave number also with the help of this equation. Here R is replaced with its value, Rydberg constant replaced with its value. So this is the wave number of the spectral lines calculated by Bohr's equation. Now we will think about the lines in the hydrogen spectrum. See here, this is the, you can see that the electron making a transition from n equal to 2 to n equal to 1, n equal to 3 to n equal to 2, n equal to 4 to n equal to 2, n equal to 5 to n equal to 2. Isn't it? So whenever the electron makes a transition from its energy level to another energy level, there corresponds a frequency or wavelength. That, see, whenever an electron makes from a transition from n equal to 5 to n equal to 2, it corresponds to a violet line of wavelength 434 nanometer and so on. Now we are going to study about the series in the hydrogen spectrum. We already know that this hydrogen spectrum consists of several spectral lines. spectral line series. And we are going to study about these spectral lines. So the first spectral line series is a Lyman series. The spectral lines in Lyman series are explained by considering that the electron falls back to n equal to 1 from higher levels. That means the electrons are coming back to n equal to 1 state from n equal to 2, 3, 4. So you can substitute n1 as 1 here and n2 can be 2, 3, 4. So from these states, electron is jumping back to n is equal to 1 state. So that series is known as Lyman series. So the Lyman series means the electron is jumping from higher energy levels to n is equal to 1 state. So that the first line means n1 equal to 1 and n2 is equal to 2. You can calculate the wave number. Now the second line is again n1 equal to 1 but n2 is equal to 3. That means from 3 to 1 transition. Again 4 to 1, 5 to 1, 6 to 1. So the electrons in the higher energy levels are making a transition from n is equal to 2 and the higher states to n is equal to 1 state. So whenever they make this transition, there forms a spectrum, and that spectrum consists of several spectral lines, and that forms the Lyman series, which can be seen in the ultraviolet region of the electromagnetic spectrum. Now the second series is Balmer series. In this series, the electrons falls back to n is equal to 2. So from n is equal to 3, 4, 5, 6, etc. the electrons are coming back to n is equal to 2 state. Again you can substitute n1 as 2 here and n2 as 3, 4, 5, etc. So whenever the electron makes a transition from n is equal to 3 to n equal to 2, that line is known as H alpha line. Now, when electron making a transition from n is equal to 4 to n is equal to 2, it is known as H beta line. Similarly, H gamma and H delta. So, these are the several spectral lines in the Balmer series of a hydrogen spectrum. You can see that from higher energy levels, the electrons are coming to the lower energy level. So, this is a emission spectrum. So, the emission spectrum corresponding to N1 is equal to 2. And this Balmer series can be seen in the visible region of the electromagnetic spectrum. Now, the third series is Paschen series, when the electron makes a transition to n is equal to 3 state from higher energy states. So, here also from n equal to 4 to n equal to 3, you can calculate a nu bar. From n equal to 5 to n is equal to 3, you can calculate the second line. And the last line, which is known as the limiting line. Limiting line means from infinity, the electron can jump back to n is equal to 3 state. That is the limiting line. You can calculate the limiting line in all the cases, like also in Lyman and Balmer. So this is the Paschen series, which can be seen in the infrared region of the electromagnetic spectrum. So whenever a transition is made, we can see a line in the hydrogen spectrum. So whenever from n equal to 4 to n equal to 3, there is an emission is made. The emission spectrum consists of a spectral line, and that spectral line having the wave number 5.33 into 10 raised to 5 meter inverse. Now, Brackett series means this is the series, line series in the spectrum, which is occurred by the electron, which is coming back to n is equal to 4th state from higher energy state. So, nu bar will be 1 by 4 square minus 1 by n square, with n2 as 5, 6, 7, etc. So, again you can see the figure from n is equal to 5, n equal to 6, n equal to 7 up to n equal to infinity. The electrons are coming back to n is equal to 4th state. So you can calculate the corresponding wave numbers as well as frequency also. Now Pfund series. In the series, the electrons falls back to n is equal to 5 state. N equal to 5 state means the higher states are 6, 7, 8, etc. So the transitions are from 6, 7, etc. up to n is equal to infinity. So you can calculate the wave number of each transition. For example, from 6 to 5. So n2 is equal to 6 and n1 is equal to 5. So you can substitute in the equation and a new bar can be calculated. Second line, from n2 is equal to 7 to n1 is equal to 5 and new bar can be calculated. And the last one is the limiting line, which is the transition from n2 is equal to infinity to n1 is equal to 5. So again you can calculate the wave number. So these are the corresponding wave numbers when an electron makes transitions from infinity to n is equal to 5. So these series of wavelengths are in the emitted hydrogen spectrum are known as Pfund series. Clear? So that's about the hydrogen spectrum having 5 series: Lymen, Balmer, Paschen, Brackett and Pfund series. Lymen in ultraviolet, Balmer in visible region, Paschen in ultraviolet, and so on. So with this we can conclude today's class. Here you can see the entire spectrum of the hydrogen atom. See, when there is a transition from to n is equal to 1, it is Lymen. Transition to n is equal to 2, it is Paschen. And n is equal to 3, n equal to 4, Brackett, n equal to 5, Pfund series. And you can see the corresponding energies of the electron in kilojoules. That is minus 13.6 electron volt. Minus 1312 kilojoule means it is minus 13.6 electron volt also. Okay, thank you.